Initial studies in the photoelastic technique seem to have been in 1937 with Heidemann and Hösch, but photoelastic visualization of ultrasound was first practically developed by Drs. Hansted and Wyatt in the UK around 1968. In the 1970s, it was popularized by Dr. Ken Hall at British Rail. The image shown is provided by Dr. Hansted and shows a multiple exposure of a 4 MHz pulse, refracted at 45 degrees. The principles are relatively simple. Pulsed light is passed from the light source at a fixed repetition frequency on the order of 100 Hz. Unpolarized light from the spark gap passes through a polarizing filter. This changes the light that passes through the polarizer to linear polarized light. This is followed by a quarter wave plate that changes the linear polarized light to circular polarized light. A second quarter wave plate and an analyzer are inserted into the light path, and the orientation configured to null the light passing through the analyzer. A clear transparent solid such as glass is inserted into the light path between the quarter wave plates. When stresses in the glass are set up by a mechanical disturbance such as our ultrasonic pulse, it causes a change in the rotation of the polarized light. Changes in stress along the light path change the conditions that nulled the light passing through the analyzer, so a small amount of light can then pass to an observer on the other side of the analyzer. By adding a delay circuit, we can adjust the position along the sound path that is illuminated by the pulse, and the camera allows the observer to record the image. A glass block was fabricated with 3 holes drilled in it. These are nominally 10 mm, 6 mm, and 3 mm diameter. An internally spherically focused probe was selected to minimize the off-axis effects. The probe used has a 12.5 mm diameter with a nominal frequency of 7.5 MHz. This compression mode element has a 150 mm radius of curvature. A refracting wedge is used to provide a shear wave beam nominally refracted at about 55 degrees from the normal. The beam was directed at the 6 mm diameter hole, and the delay increased to observe the interactions. At about 3.8 microseconds after the element has been pulsed, the mechanical pulse enters the glass from the wedge. The incident angle is greater than the first critical angle, so only a shear mode is present in the glass. After entering the glass and moving about halfway towards the hole, the pulse image is approximately 5.3 microsecond delay from the entry point. As the delay is increased, we see the pulse maintaining an almost plane wavefront that narrows slightly as the target is approached. As the plane wavefront hits the glass-air interface, the reflection process begins. The first point of contact occurs such that the incident shear wave makes a perpendicular incidence at the closest point on the whole surface. This will result in a maximum reflected pressure of a shear wave moving directly back along the incident path. As the incident plane wavefront of the shear wave advances, the angle made with the rounded surface of the hole ensures that no other part of the plane wavefront can be perpendicular to the whole surface. Therefore, all other points of the shear wavefront impinge at angles greater than 0. This angle increases until the wavefront is at the halfway point of the hole. Here, a glancing incidence occurs. The reflected transverse wave that forms as a result of this interaction takes on the cylindrical shape of the hole as it propagates away from the reflecting surface. But at any angle away from the perpendicular, an incident shear wave at a solid to free boundary interface will mode convert, and, in addition to the reflected shear wave, a reflected compression wave occurs. The compression wave moves off in a similar cylindrical shape, but at about twice the shear velocity. The associated wavelength of the two modes, as well as their positions in time and distance from the target, can be used to verify the modes. The wavelength of the shear mode is measured at about 0.5 millimeters, and the compression mode is about 0.8 millimeters. As the shear wavefront progresses, the second critical angle is reached at the curved surface, and a Rayleigh wave forms. The Rayleigh wave is seen linked to the interaction of the shear mode with the free boundary. The linked wavefront can be considered a form of head wave, and it has the appearance of a spiral. This head wave can be seen to account for the post-cursor signals that an ultrasonic technician sees as repetitions on the A-scan, as a result of several circuits around the cylinder. We would like to acknowledge the interest and support provided by Dr. P. D. Hanstead.